Good morning. I am Dr. P.Suresh Pandiarajan, Associate Professor in EC Department at P.S.R. Engineering College. Now we are going to discuss about basic introduction about logic gates and the multiplexers. Now, so logic gates. So logic gates are the basic elements that make up a digital systems. So you have to design any logic circuits by using gates. Without using gates, you cannot design any digital logic circuits. So the electronic circuit is a circuit or gate is able to perform some binary inputs and produces some logical output functions. So the basic gates are AND, OR, third one NOT gate. So these three gates are basic gates. Again, NAND gate, second one NOR gate. These two gates are called as universal gates. Third one others. XOR gate and exclusive NOR gate. These two gates are called as other gates. First of all, and then why we are calling NAND and NOR gates are called as universal gate means why? Because we are using these two NAND gates. By using two NAND gates, NAND and NOR gates, we can implement any basic gates like AND gate, OR gate, NOT gate, XOR gate and exclusive NOR gate. So this is the main concept of universal gates. That's why we called as universal gates. NAND and NOR gate also called as a universal gates. First one, let us see about the NOT gate. So the basic operations of NOT gate. So NOT gate performs inverse operation. So inversion or complementary functions. So this is the logic diagram or symbol. So it has only one input A and output produces A bar. So truth table. So A and A bar. This is for input. So this is for output. So input 0, output 1. Input 1, output 0. When we are giving input 0, the output becomes high. When you are giving the input low, high, the output becomes low. So this is the basic concept of NOT operation or inverse operation or complement operations. So A equal to A bar. A bar means inverse operations. Next one, AND gate. AND gate. So AND gate is a logical operation that performs multiplication operations. So we can write as Y equal to A dot B. So dot indicates multiplication. Y is the output response and you are giving the two inputs. So AND gate operation, two or more inputs but single outputs. So this is the basic symbol of AND gate. It has two inputs A and B, output Y equal to A dot B. It can represent truth table A, B, A dot B. So the truth table represents the relationship between input and output side. If you are giving two input means four possible combinations, that is 0, 0, 0, 1, 1, 0, 1, 1. These are the four possible combinations. 0 into 0, multiplication operation, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1. So the operations of AND operation says that when both inputs are high, the output becomes high. When any one of the input is low, output automatically low. So this is the AND operations. AND operation. Next one, OR gate. So OR gate, the logical operation, it performs addition operation. So that is y equal to a plus b. It has two or more inputs but single output only, except NOT gate. Any other logic gates having more than n number of inputs but single outputs. First draw the logic diagram. So this is the logic diagram of OR gate a plus b. It performs addition operation. So a, b, y equal to a plus b. Truth table a, b, again a plus b, 0, 0, 0, 1, 1, 0, 1, 1. So 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 1. So the operation says that, OR operation says that when both inputs are low, the output becomes low. When any one of the input is high or low, the output becomes high. So this is the major concept of OR gate. Next one, NAND gate. So NAND gate means, simply says that it performs inverse operation of AND gate. So y equal to a dot b inversion whole bar. This is called as NAND gate. So symbol of NAND gate, draw the first AND gate, simply put one invert operations called as NAND gate. So a, b, y equal to a dot b whole bar. It's inverse operation of AND gate. So a, b, we can represent it as a NAND gate by truth table y equal to a dot b whole bar. So here also common for 0, 0, 0, 1, 1, 0, 1, 1. 4 possible combinations of inputs and produces output for 0 into 0, 0, but inverse operation 1. 0 into 1, 0, inverter 1. 1 into 0, 0, invert operation 1. 1 into 1, 1, inverse operation 0. So the operation NAND operation says that when both inputs are high, output becomes low. When any one of the input is 0 or 1, output becomes high. So this is the NAND operations. Next one, NOR gate. So NOR means it's inverse operation of OR gate. Here also a plus a, b is the two inputs, a plus b whole bar is the two outputs, 0 into 0, 0, 0 plus 0, 0, inverter 1, 0 plus 1, 1, again inverter 0, 1 plus 0, 1, inverter 0, 1 plus 1, 1, inverter 0. So the operation says that both inputs are low, output becomes high. Remaining are zeros. When any one of the input is high or low, output becomes low. So this is the NAND and NOR gates called as universal gates. Why we are calling universal gate means already know that by using these two NAND gates we can implement or realize any logical functions like NOT gate, AND gate, OR gate, like that. Next one, exclusive OR gate. Exclusive OR gate, these are other gate functions. So y equal to a exclusive b, y exclusive b. So this indicates for exclusive OR gate. So this can be written as y equal to a bar b plus a b bar. This expansion of a exclusive b is equal to y equal to a bar b plus a into b bar. So this is the logic symbol of exclusive OR gate. So a b, y equal to a exclusive b. So this is the logic symbol of exclusive OR gate. Now we can write as truth table for exclusive OR gate A, B, again A bar, B bar, A bar B, A B bar, A bar B plus A B bar. So, two inputs 0 0, 0 1, 1 0, 1 1. So, this is the common operations, common inputs for possible combinations of two inputs 0 0, 0 1, 1 0, 1 1. So, A bar means 1 1 0 0. B bar inverse operation of this one 1 0 1 0. So, A bar into B. So, A bar into B. So, multiplications of these two numbers 1 into 0 0, 1 into 1 1, 0 into 0 0, 1 into 0 0, because this is AND operations. Again A into B bar. So, A here B bar 0 into 1 0, 0 into 0 0, 1 into 0 0, 1 into 0 0, right. Now adding these two numbers, because A bar B plus A B bar. So, A bar B plus A B bar means 0 plus 0 0, 1 0 0. So, this is for, so A B, A bar 1 1 0 0, B bar 1 0 1 0, A bar into B 0 1 0 0, A B bar 0 0 1, sorry, here 1, so 1. So, the exclusive OR gates A bar B plus A B bar equal to 0 1 1 0. So, this is operations of exclusive OR gates. Like next one, last one, exclusive NOR gate. So, exclusive NOR gate means that's just inverse operations of exclusive OR gate. So, A exclusive B whole bar, that's all. Y equal to A exclusive B whole bar. Just exactly says that simply you got to put one inversion symbol of exclusive OR gate, Y equal to A exclusive B whole bar, Y equal to A exclusive B whole bar. So, this can be written as Y equal to A bar B bar plus AB. So, this is the expressions for exclusive NOR gate, Y equal to A bar B bar plus A into B. So, here A bar B bar A bar B bar AB. So, A bar B bar means 1 into 1 1 0 0 0, AB multiplication of two numbers A and B 0 0 0 1. Again adding these two numbers A bar B bar plus AB, adding two number 1 0 0 1. So, just exactly reverse operations of exclusive OR gates. So, this is called as exclusive NOR gates. Now, we are going to design about universal gates. Just simply one example says that design AND gate, design AND gate using only NAND gates. So, we can realize any logic gates by using NAND gates. First example, AND gate. Step number 1, draw the logic diagram. So, first draw the logic diagram means you have to draw the AND gate. So, A, B, Y equal to A dot B. Again, you got to design AND gate using only NAND gate means you got to just adding bubble of the inverter output side. This is for second step. First step, draw the actual diagram. Second step, you got to adding bubble for the output side of AND gate. Third step, where you got to adding this bubble, after that you got to adding inverter. Just you got to adding one more inverter. Again finally, fourth step for you got to replace all the gates are NAND gates. So first one NAND gate, just you got to replace by NOT gate, 2 input AND gate. So A, B, so this is for Y equal to A dot B whole bar. So this is for best example for design AND gate using only NAND gates. So this is also NAND gate, this is also NAND gate. So the output performs NAND gate operations, Y equal to A dot B, Y equal to A dot B. This is the output operations of Y equal to A dot B is the AND gate operations. Next one, design AND gate, design OR gate. Design OR gate using only NOR gate. So first step number 1, draw the actual diagram OR gate. So Y equal to A plus B, here also A and B. Step number 2, you got to adding bubble of the output side because you are using OR gate and NOR gate. So OR, NOR means output side, AND means input side. So A, B. Third step, you got to adding one more inverter for the after bubble A, B. First, second step, this is for third step. Fourth step, you got to replace all the gates are NOR gates. Y equal to A plus B. So this is for realize OR gate using only NOR gates. So this is the best example of universal gates. Next one, multiplexers. So multiplexer is a digital switch. It allows digital information from several sources to be routed on a single output line. So the basic multiplexer has 2 power n input lines and one single output line. So the particular input line is controlled by a set of selection lines whose bit combinations are determined. The particular input is selected. So the basic multiplexer has 2 power n input lines, where n is the number of selection lines. N is the number of selection lines. So this is the basic block diagram of multiplexer. Single output Y, input for D0, D1 up to D power n minus 1, selection lines S0, S1 up to S0 power n minus 1. So this is the basic concept of multiplexer. So multiplexer also called as a data selector. Data selector because of in multiplexer the output always depends upon only selection line, not depends upon input lines. Because the basic multiplexer has several data input lines but single output line. The particular input line is controlled by a set of selection lines. That's why we can call as data selector. Multiplexer also called as a data selector. For example, 4:1 multiplexer. Design 4:1 multiplexer. So design 4:1 multiplexer means formula 2 power n:1. So 2 power n:1 means this is the best formula for multiplexer. So n is the number of selection lines. So here 4 inputs. So 2 power 2:1. So number of selection lines are 2 selection lines. 2 selection lines. So this is the basic logic diagram of 4:1 mux and single output Y. So here D0, D1, D2, D3. So this is the input for multiplexer. 4:1, 4 input lines, 2 selection lines, that is here S0 and S1. S0 and S1. So 4 input lines, single output line, 2 selection lines, because of our formula is 2 power n is to 1. So S0 and S1. So the particular output line is controlled by a set of 2 selection lines by using 4 input lines. Not depends upon output, always depends upon only selection lines, not depends upon input lines. So this is the main concept of multiplexer. Now the relationship between input and selection lines and output for, so input lines and output response for here 2 selection lines S0, S1 and Y. So here 2 selection lines S0, S1, output response Y. So 2 selection line means there are 4 possible combinations of input lines. So 0, 0, 0, 1, 1, 0, 1, 1. So this is the selection lines. Suppose you go to first D0, D1, D2, D3. First you have to select for S0, S1, 0, 0 means first data inputs D0 will be selected. D0 will be selected. Again 0, 1, S0 low, S1 high means 0, 1 for D1. 1, 0, S0, 1, S0, 1, S1, 0, D2 selected. Again S0, 1, S1, 1, D3 selected. D3 selected. So the output will be written as Y equal to D0 S0 bar S1, because 0 means S0 bar, here also S1 bar, 0 for S1 bar. So Y equal to D0 S0 bar S1 bar plus D1 S0 bar S1 plus D2 S0 S1 plus D3 S0 S1. So this is the final expressions for 4:1 multiplexer. Y equal to D0 S0 bar S1 bar plus D1 S0 bar S1 plus D2 S0 S1 bar plus D3 S0 S1. Now you have to design the 4:1 multiplexer. S0 S0 bar, S0 S0 bar, again S1 2 selection lines, so S1 and D1 D2 D3, D1 D2 D3, so D0 D1 D2 D3. First one Y equal to D0. So D0 S0 bar S1 bar by connecting to performs AND operations plus D1. So D1 S0 bar S1 again third one D2. So D2 S0 S1 bar. Fourth one D3 S0 S1. So S0 S1. So it performs 4 AND gate operations and then connecting 4 AND gate by a single OR gate output Y. So this is also called as a 4 input lines, 1 single output lines, 2 selection lines. So the multiplexer says that 4 input lines, 4:1 multiplexer, 4 input lines, 2 selection lines, single output lines. So this is also called as a 4:1 multiplexer. So, and also we can implement any logic function 2:1 multiplexer, 8:1 multiplexer, 16:1 multiplexer, whatever it is. Thank you.